Welcome to Spring LIB.
Okay, so today we're going to be comparing the wavelengths of an alpha particle that has an energy of 25 MeV, and a proton, the wavelength of a proton that has the same energy of 25 MeV. Okay, and we're going to be comparing that to a nucleon, the wavelengths to nucleon that has a size of about 1.6 times 10 to the negative 15 meters, or 1.6 femtometers. Okay, so we're going to be using our trustworthy equation here of the wavelength equals Planck's constant over the momentum. And we know that momentum equals the square root of 2 times the kinetic energy times the mass of the particle. And combining these two together is going to give us wavelength equals Planck's constant over 2 times the kinetic energy times the mass. Okay, so let's remember that H equals 6.626 times 10 to the negative 34 joule seconds. Okay, joules per second. And this is the de Broglie wavelength here. Okay, so let's start off with our alpha particle, plugging that in to our equation. To simplify here, I'm going to leave that as H, and then over 2 times the mass. So we want that in terms of kilograms because we're working in joules and seconds. So 2 times 6.64 times 10 to the negative 27. Let's make this longer. Kilograms times the energy. And so 25 MeV is 25 times 10 to the 6, 25 times 10 to the 6 eV, but we want this in terms of joule, so we're going to multiply that by 1.6 times 10 to the negative 19 joules per second. Okay, and when we plug everything in and calculate that all out, that's going to give us an answer of 2.87 times 10 to the negative 15 meters. Alpha particle. Okay, we're going to do the same exact thing for the proton. And H is going to stay the same, Planck's constant. Our energy is going to stay the same, 2 times K. The energy is going to stay the same. The only thing that's going to change is the mass, and that's going to be 2.167 times 10 to the negative 27 kilograms. And when you calculate that all out, we're going to get an answer of 5.7 times 10 to the negative 15 meters. Okay. And now, comparing this to our nucleon, the size of a nucleon, we can immediately see that the alpha particle is closer in size, and therefore the alpha particle, the wavelength, is closer in size to the size of a nucleon. So we know that the alpha particle, let's get rid of some of that, the alpha particle is better at resolving. The nucleon. Okay, and we can also do a quick calculation to show that the alpha particle wavelength is about 1.8 times the size of the nucleon as such, and the proton is about, the wavelength of the proton with this energy is about 3.6 times the size of the nucleon. 3.6.